Hello everyone, welcome back to a new lecture of thermodynamics. I am Dr. Mohammad Uzair, and today we are going to start the chapter number 10, which is vapor and combined power cycles. So basically we are going to study the steam power plant or the steam power cycles in this chapter. First of all, when we are going to talk about any ideal cycle or the most efficient cycle, so as we know that the Carnot cycle is one of the most efficient cycle operating between two given temperature limits. So whenever there are two temperature limits, the Carnot cycle will give you the maximum efficiency. It will give you the maximum efficiency. It will not give you the 100% efficiency. There is a difference between the 100% efficiency and the maximum efficiency. So Carnot cycle is the most efficient cycle. So if the Carnot cycle is the most efficient cycle, so it is the first choice to use in vapor power plants, so that we will get the maximum power output. Now we are going to discuss about the Carnot vapor cycle. We know about the Carnot cycle, so now we are going to fix the Carnot cycle to operate by using the vapors. So let's suppose we have a steady flow Carnot cycle executed within the saturation dome of pure substance, as you can see in the figure. So we have the TS diagram here, and we have basically fixed the Carnot cycle within the saturation dome, and we are assuming that the working fluid is a pure substance, and in this case we are assuming the working fluid as water. Now the fluid is heated reversibly and isothermally in the boiler, which is this process, the process 1 to 2. So this is the process where there is Q in by boiler, and then this heated vapors that are going out from the boiler at point number 2 will be expended isentropically, because you can see we have a isentropic line. The entropy of the process is constant, so the entropy at point S2 and S3 both are same. So the water vapors are going to expand isentropically in turbine. So this is the process of the expansion, or we are going to get the power here because we are using the turbine. 3 to 4 is the process in which the water vapors will condense, and this condensation process take place reversibly as well as the isothermally, and the device that we are going to use for this condensation is basically called condenser. So we have the condenser in this process between process 3 to 4, and then we have to basically compress, or we have to increase the pressure of the water vapors. So either we have to use the compressor. So let's say we are going to use the compressor from 4 to 1, and this process should be isentropically. You can see the entropy of S4 and S1 both are same, because this is the Carnot cycle, and we are going to fix that. We are going to fix this Carnot cycle in this dome. So we have basically placed our Carnot cycle within this saturation dome of pure substance. Now what will happen? There are several issues associated with this case. So we are going to discuss the different issues. So first one is, If you can see here, the isothermal heat transfer to or from a two-phase system is not difficult to achieve in the practice, since maintaining a constant pressure in the device automatically fixes the temperature at the saturation value. So you can see here we have the heat addition process, which is the process 1 to 2. Even the heat addition process is also an isothermal process, because as we know that if we have the constant pressure and we are basically in the dome, so with respect to pressure the temperature will be constant. So here if the pressure is constant, then you will get the isothermal process between 1 and 2. Similarly, the 3 to 4 will be an isothermal process. So the process 1 to 2 and 3 to 4, they can be approached closely in actual boiler and the condenser. So there is no issue with these two processes. So we have the two processes, 1 to 2, which is basically the boiler, and 3 to 4, which is basically the condenser process, and we can achieve these processes in the real life. So when we are going to limit the heat transfer processes to two-phase system, it will basically limit the maximum temperature that can be used in this cycle. Because if we are going to use the Carnot cycle here in this dome, you can see here this dome, so our maximum limit, because we are saying that we are basically trying to transfer the heat to or from a two-phase system, so it means we can maximum go up to this limit. Maximum we can go up to this limit, which is called the critical limit. So for water we have the critical limit, which is 374 degrees Celsius, because this is the critical point for the water. So the maximum limit for vapor power cycle will be 374. So it's mean if we are going to limit the temperature, so it's mean you are going to limit the efficiency as well, the thermal efficiency, because we have the maximum temperature of 374 in this case, and we have the minimum temperature. So when we are going to check the efficiency, so it will be in between these two temperature limits. One is somewhere here and the last one is somewhere here. So if you are going to increase the temperature, so any attempt to raise the maximum temperature in the cycle involves heat transfer to the working fluid in single phase, because if this line, this 1 to 2 line is above this, if this is above this one, so it's means there is basically a single phase, which is not easy to accomplish isothermally. The heat transfer in two phase is easy to maintain isothermally, but it's not easy to maintain the transfer of heat isothermally in single phase. So this is the issue. So we have two issues here. We have one issue that we cannot shift this 1 to 2 somewhere here above the critical point, and secondly, if we are using the Carnot cycle, so it's mean we are basically going to limit our efficiency related to the critical point temperature. Moving further, when we're talking about the process 2 to 3, the process 2 to 3 is basically the isentropic expansion, and normally the well-designed turbines can achieve this isentropic expansion process. So we can achieve this one in the well-designed turbine. So we can get the isentropic expansion in the turbine. But the issue is, if you can see here, this point number 3 is in between, or especially in between this dome. So it's been at point number 3 or at the exit of this turbine, we will get the vapor liquid mixture. So it's means there is the quantity of water. So at the exit of the turbine, or even during this process, the turbine blades will experience the water vapors, and the water vapors are basically going to damage the blades, which is not acceptable. Normally it is recommended to use the superheated steam in the turbines, and if we are going to fix fix the Carnot cycle here, so you can see here that the quality of this steam decreases during this expansion process, as you can see here. Thus, the turbine has to handle the steam with low quality, that is the steam with a high moisture content. So it's mean these water vapors basically will provide a corrosion and the erosion to the turbine blades, and it is not recommended to use the water in the turbine. Normally, in the power plants, it is a normal practice that the steam with qualities less than about 90% is not allowed. Means the steam with qualities less than about 90% means that the 3 point, at this point the quality should be more than 90%. So here we can achieve the isentropic expansion in the turbine like this one, but the issue is the water vapors if we are going to use the Carnot cycle in this dome. So this is a dangerous thing for the power plant. Now the isentropic compression, which is this one, the 4-to-1. Now the isentropic compression involves the compression of a liquid vapor mixture, because at point number 4 we have the liquid vapor mixture, and we have to compress it up to saturated liquid. So at point number 1 we have the saturated liquid. So basically there are two different difficulties involved in this process. First of all, it is not easy to control the condensation process so precisely as to end up with the desired quality at state number 4, because we have the condenser here, so it's not easy to control the condensation process. And secondly, it is not practical to design a compressor that handles two phases. Here please remember, the compressors are designed to compress the gases, while in order to increase the pressure we use the pump. So due to these reasons we cannot operate the Carnot cycle within the saturation dome. There is another possibility to operate the Carnot cycle like this one. As you can see here with the TS diagram, and the process 4-to-1, 1-to-2 and 2-to-3 are basically outside from the dome. Now here some of these problems that we discussed in the previous slides could be eliminated by executing the Carnot cycle in a different way, as you can see here. But the problem is it's very difficult to maintain the isentropic expansion. The compression. This one, the isentropic compression to extremely high pressure, and the isothermal heat transfer at variable pressure. The isothermal heat transfer using a single phase is very difficult to maintain, as well as the isentropic compression, this one, is very difficult to maintain, because you have to compress it from here to extremely high pressure. So here, if you can see here, thus we conclude that the Carnot cycle cannot be approximated in actual devices, and it is not a realistic model for vapor power cycle. So that's mean we cannot use the Carnot cycle in vapor power cycles. So what we do? The problem with the Carnot cycle is that we have to limit the moisture content here, as well as we have to shift this one somewhere here, so that we can easily pump the liquid. So what we do, we simply modify our Carnot cycle. So we define a new cycle which is called the Rankine cycle. This is the ideal cycle for vapor power cycle. So many of the impracticalities associated with the Carnot cycle can be eliminated by superheating. You can see here we are going to superheat. Sorry, by superheating the steam in the boiler. So we are not going to stop here. We are basically going to superheat up to this point. So we are going to superheat the steam in boiler and then condensing it completely in the condenser. So you can see here I'm going to condense completely in condenser. So what will happen in this way, when we are going to superheat the steam up to this point, then from here to here we have turbine. So turbine, in the turbine the working fluid will be in superheated region, and you can see here the point number 4 is very close to the saturated vapor line, which means the quality is very high here. And as mentioned here, the condensing is completely performed in the condenser. So we are not going to stop somewhere here, rather than we are going to condense the working fluid up to saturated liquid line. Now from here we can easily pump, and we will use a pump here rather than a compressor. So this is the schematic diagram. We have a pump to pump the boiler, pump the working fluid, which is water, up to the boiler pressure. And here we have boiler, which will be operated at constant pressure. And then we have the turbine, steam turbine. So steam turbine will get the high pressure, high temperature steam from the boiler, and it will expand, the steam will expand in the turbine, and it will rotate the shaft, and then we will get the power. So from 4 to 1 we have the condenser process, where the heat rejection process will take place. So here if you can see, we have the Wn in the pump. So here we have the pump work input, then we have the Qn in the boiler. So we are basically transferring the heat in the boiler. Then we have the turbine work output. So we will get some work output from turbine, and then we have some Q out from the condenser. So here basically when we are talking about the ideal Rankine cycle, so ideal Rankine cycle for vapor power plant basically consists of 4 different processes. The first one is, which is basically the work done, work input to the pump, is basically isentropic compression in a pump, which is process 1 to 2. Then we have 2 to 3, which is constant pressure heat addition in boiler. Then 3 to 4 is the isentropic expansion in the turbine, and then we have 4 to 1, which is the constant pressure heat rejection in the condenser. So we have basically 4 different processes for an ideal Rankine cycle. So here, when we are talking about the state number 1, which is somewhere here, this one. So you can see here the water enters the pump at state number 1 as saturated liquid. So remember, the water will enter the pump at state number 1 as saturated liquid. So you can find the properties of the saturated liquid from the steam table using the temperature table, and the properties will be like, if you have to find the enthalpy, then it will be HF at the given temperature, the VF V will be VF at the given temperature, the S will be SF at the given temperature. Now the when the water is going to enter in the pump at state number 1, so it will be compressed isentropically to the operating pressure of the boiler. So here we can see we have 2 different pressure lines. We have this one, which is the boiler one, and we have this one. So basically the Rankine cycle operates between 2 different pressure lines. So we have the point number 1, and then we are going to compress the water, or basically we are going to increase the pressure of the water isentropically to the operating pressure of the boiler. So basically this is the operating pressure of the boiler. So this is point number 2. The water temperature increases somewhat during this isentropic compression process due to a slight decrease in the specific volume of the water. So you can see there is a specific change in the specific change in the volume. So there will be a slight increase in the temperature. Now, the vertical distance between state 1 and 2 on the TS diagram is basically greatly exaggerated for clarity. Otherwise, you will get a very small line between 1 and 2. Now, at point number 2, the water enters the boiler as compressed liquid. The water enters the boiler as a compressed liquid at state number 2 and leaves as a superheated vapor at state number 3. So remember this thing. This point number 2 is basically the compressed liquid. This is the entry point of the boiler, and it will leave at point number 3 as a superheated vapor. The boiler is basically a large heat exchanger where the heat originated from the combustion gases or like nuclear reactors or other sources is transferred to the water essentially at constant pressure. So you will get a source here, the combustion source. It will transfer the heat to this water, and the water will be heated from this point, which is the compressed liquid, to this point, which is basically the superheated region or superheated steam. And this whole process will take place at constant pressure. Now remember, the boiler together with the section where the steam is superheated is often called the steam generator. Now, after from point number 3, which is the exit point of the boiler as well as the entry point of the turbine. So the superheated vapor at the state number 3, somewhere here, enters the turbine where it expands isentropically. Isentropically means the entropy is constant. It will expand isentropically and produces work by rotating the shaft connected to an electric generator. The pressure and the temperature of steam drop during this process to the value at state number 4. So you can see we have the state number 4 here. At the exit of turbine, which is point number 4, we will get the steam as saturated liquid vapor mixture with a high quality. So here, as you can see, the steam is expanding in basically superheated region. So at point number 4, you will get the saturated vapor mixture with high quality. The point number 4 is also the entry point to the condenser. So steam is condensed at constant pressure in the condenser, which is basically a large heat exchanger. By rejecting heat to a cooling medium such as a lake, a river, or to the atmosphere, the steam leaves the condenser as saturated liquid and then enters to the pump, completing the complete cycle. So we have the complete cycle in which we have the pump, boiler, turbine, and then we have the condenser. Now moving to the next slide, but before going to next slide, here if you can see the TS diagram. So we have the process 421, which is the Q out to the water or lake water or the river or the atmosphere. So this is basically the Q out, the heat rejection, and here we have the Q in. As we know, the area under the curve on the TS diagram is equal to the heat. So basically we have two different heat. One is this one. So if I'm going to check the area under the curve on a TS diagram between process 2 to 3, then I will get the heat transfer to the water in the boiler, and the area under the curve for process 4 to 1 will represent the heat rejection in the condenser. Now remember that the difference between these two heat transfer will give you the net work done during this process. So normally the work net is the difference of Q in and Q out. So Q in minus Q out will be equal to the work done, and this is basically work net, the total work. If you see here in system, during this Rankine cycle process, we have the work in and we have the work out as well. So the total W net is the W out minus W in, because this pump is going to consume some work and this turbine is producing the work. So total net is the output minus the input, and then you will get the W net. Or you can get the W net by using Q in minus Q out, as you can see here. So here we have the energy analysis of the ideal Rankine cycle. All the four components associated with the Rankine cycle, the pump, boiler, turbines and the condenser, are basically the steady flow devices, as you already studied in chapter 5. And thus all four processes that make up the Rankine cycle can be analyzed as steady flow processes, because we have all these steady flow devices. So the Rankine cycle is basically consists of steady flow processes. Normally the kinetic and potential energy changes of the steam are usually small relative to the work and heat transfer terms, and are therefore usually neglected. Now when we talk about the steady flow energy equation per unit mass of the steam, so after neglecting the kinetic energy and the potential energy, we will get the equation like this one. We have the Q in minus Q out plus W in minus W out equal to the change in the enthalpy. So we have the enthalpy change here, but here if you see, we don't have any kinetic energy and we don't have any potential energy. So we have the inlet and the exit enthalpies. Now we have the boiler and the condenser. In these two processes, during these two processes, there is no work done, or basically these two devices do not involve any work. On the other hand, when we are talking about the pump and turbine, they are assumed to be isentropic. Thus we can easily write down the energy equations for these four different components. So first of all, when I'm saying the pump is basically assumed to be isentropic. Normally it's adiabatic as well, so there is no Q involved during pump, so Q is 0. So in the pump there is no work output as well. So the steady flow energy equation that we studied in the last slide will be reduced to this one. We will have the W pump in, because there is no Q in and there is no W out. Then this W pump in will be equal to H2 minus H1, or if you remember the chapter number 7, we have the pump work in is equal to V P2 minus P1, where V is basically equal to V1 or Vf at the given pressure, and H1 is Hf at the given pressure. So we can easily equate the H2 minus H1 equal to V P2 minus P1 as well. So this is the pump work, which is basically the input to this Rankine cycle. For the boiler, there is no W out. There is no W involved. So there is no work in, there is no work output. Only we have the Q in, there is no Q out as well. So using the steady flow energy equation, we will get the Q in is equal to H3 minus H2, because we have only the enthalpy change here. So you can see we have the only enthalpy change H exit minus H in. So we don't have any work and we don't have any Q out, so we have only Q in for boiler. For turbine, we normally say that it's the isentropic process as well as the adiabatic as well. So Q is 0. There is no Q, so so there is no Q in, Q out. In the turbine, we normally get the work output, so there is no Q. There is no W in as well. So the equation will be reduced to give you this formula, which is the turbine work out is equal to H3 minus H4. Similarly, for the condenser doesn't involve any work, and there is no Q in as well because only Q out is observed during the condensation process. So, using the energy equation, the steady flow energy equation, we will get the equation like this one: Q out is equal to H4 minus H1 for the condenser. So we have the pump, we have the equation H2 minus H1 in terms of enthalpy, which is also equal to V P2 minus P1. For boiler, we have Qn is equal to H3 minus H2. For turbine, we have W turbine out, which is H3 minus H4, and we have Q out, which is H4 minus H1. Now, the W net will be equal to either this minus this or Q in minus Q out. So in both cases, you can find the W net. So the thermal efficiency of the Rankine cycle is determined from this formula, which is the thermal efficiency of the cycle, which is W net upon Q in. So I know W net is Q in minus Q out. So by putting the value of Q in minus Q out and then making the LCM, then you will get 1 minus Q out upon Q in. So we know the Q in, Q out formulas. We can easily get these values, and then we can find the efficiency, or the W net equal to the work turbine out minus work pump in. So in both cases, you will get the same W net, because we have to find the W net here and Q in, and then we can easily find the efficiency. But here we have some interesting thing. When we talk about the USA, in USA, the conversion efficiency of the power plant is often expressed in terms of heat rate, which is the amount of heat supplied in BTUs to generate 1 kilowatt hour of the electricity. So normally the conversion efficiency is defined in terms of the heat rate rather than thermal efficiency. So smaller the heat rate, the greater the efficiency. So this is on the this phenomena. You can observe this phenomena in USA only. Otherwise, normally we define the thermal efficiency by using this formula. Now we have a problem. This is a simple problem here. So in this question, we have a steam power plant operating on the simple idler Rankine cycle. Now the steam enters the turbine at 3 megapascal and 350 degrees Celsius. So you can see here for the turbine we have 3 megapascal and 350 degrees Celsius, and is condensed in the condenser at a pressure of 75 kilopascal. So you can see we have two pressures. We have 75 kilopascal and we have 3 megapascal. During the boiler, we have the constant pressure. So at point number 2, we will get the same pressure. And during condensation process, we have the constant pressure. So at point number 4 and point number 1, we will get the same pressure. Now, we have to find the thermal efficiency of the cycle. First of all, we are going to draw the TS diagram for this cycle. So you can see here we have the TS diagram. We have two different pressure lines. One is the condenser pressure line, which is the 75 kilopascal, and we have second one, which is the 3 megapascal, and the boiler pressure line. So you can see we have another pressure line, 3 megapascal. Now we have the point number 1 and point number 2, the process line. Remember, this is the complete vertical line in a straight line, because the entropy is constant. So at point number 1 and point number 2, the entropy is constant. Same way, 3 and 4 is basically is a straight line, and the entropy is constant at point 3 and point number 4. We're talking about the simple ideal Rankine cycle. Now, basically we have to find the thermal efficiency, and for thermal efficiency, there is a need to find the W net and Q in or the Q out. So as we know, we have the W in here for the pump, we have the Q in during the boiler process, we have the W out through the turbine, and then we have the Q out through condenser. So basically, when we are going to solve the ideal Rankine cycle, we have to find the enthalpies at all these points. So we have the point number 1, point 2, point 3, and point 4, and then we will get the enthalpy values at all these 4 points. And then we have the simple formulas. So at state number 1, we have 75 kilopascal and saturated liquid. Remember, always we will get this saturated liquid at the start of pump. So this is the 75 kilopascal and the saturated liquid. So here we have the 75 kilopascal and the saturated liquid. So when we have this data, so we can easily find out the H1, which is the HF at the 75 kilopascal. After finding out the value of H1, we can easily find out the value of V1 as well. The V1 will be Vf at the given pressure, because we have the pressure value, so we can easily check the V1 and H1. As well as if we have to find the temperature at the point number 1, so it will be the T saturation at the given pressure, which is around 91.76 degrees Celsius. Now we know the properties at point number 1. The state number 2 is basically the compressed liquid, and we know that the pump work is equal to V P2 minus P1. So it's been by putting the value of V1 from here, and we know the P2 and P1. So P2 is 3 megapascal, so converting into kilo, and this is 75 kilo. So at the end you will get the answer in kilo, and then by solving this one you will get the 3.03 kilojoule per kg. So this is the pump work input. Now remember that the pump work input is also equal to H2 minus H1. So by rearranging the equation, H2 will be equal to H1 plus the work of pump in. So I know what is H1. H1 is 384.44, and then we have to add the pump work input, which is 3.03. So H2 will be 387.47. So we know what is H1, we know what is H2. Now for the value of H3, we know the state number 3. The state number 3 is the, at state number 3 we have the pressure of 3 megapascal and the temperature of 350 degrees Celsius, which is already given in the question. So when you will check the 3 megapascal and 350 degrees Celsius, you will find that the state is basically in superheated region. So using the superheated table, which is the table A6, you can easily find out the value of H3, which will be equal to 3116.1 kilojoule per kilogram. At the same point, I'm also going to check the S3 as well. Remember, this is recommended to check S3 at the exit of boiler, because at point number 4, the S4 will be equal to S3. The S4 will be equal to S3 as given here. So at state number 4, we have the pressure of 75 kilopascal and S4 is equal to S3. Now, first of all we have to check the state or the phase description. As we know, we have the pressure of 75 kilopascal. So at the 75 kilopascal, we can check the SF value and SG value. And if the given value is more than SG, then state 4 is still in the superheated region. But in our case, the value of S4, which is 6.745, lies between SF and SG. So you can see here is 1.2 and this is 7.4, and we have the 7.6. So it's somewhere in between SF and SG. So it's mean the state of 4 is basically the liquid vapor mixture. So if the state 4 is liquid vapor mixture, then we can easily find out the quality. We can easily find out the quality of the steam. So it will be, we have the formula like S4 is equal to SF plus X SFG. So by rearranging the formula, we will get the x4, which is S4 minus SF upon Sg minus SF, or SFG. So by putting the values, you will get the x value of 0.886. So in this case, we are getting the x value of 0.886. The question is why we are going to find the value of x4. We calculated the value of x4 in order to get the value of h4, because h4 will be equal to hf plus x hg minus hf as written here. So h4 will be hf plus x for hg minus hf. So we know what is the quality at point number 4, and value of hf and hg we can easily get from the stream table at 75 kilopascal. So just by putting the values, we will get the h4 value, which is 2403 kilojoule per kilogram. Now we have the enthalpy values at all points. Now using the basic formula, we can easily calculate the Qn. The Qn will be H3 minus H2. So we know what is the H3, we know what is the H2, so we will get the answer. Q out will be H4 minus H1. Just simply putting the values, we will get the answer. Therefore, the thermal efficiency will be 1 minus Q out upon Qn, and then we will get the 26% efficiency. We can find out the efficiency with the help of W net as well. Instead of using this one, we can find out the W net, which is the W turbine out minus W pump in. So W turbine out will be H3 minus H4. Remember, always we have to subtract from the higher value. So H3 is higher because we have the 3116, and H4 is we have the less value for the H4, which is 2403. So we will get 713. So this is the turbine out. Already we know what is the pump input, which is 3.03. We already calculated W pump in the start. So we have the W net, which is equal to W out minus W in, and we will get 710.07. And using this formula, which is W net upon Q in, we will get the same answer, which is 26%. So in both cases, we are getting the 26% efficiency. Here we can compare this one with the Carnot cycle as well. It is not given in. It is not asked in the question to find out the Carnot efficiency, but we can find out the efficiency. So here, if we have to find the Carnot efficiency, so we need two temperatures: the temperature minimum and temperature maximum. We know the temperature maximum for this cycle is the 350 degrees Celsius. So 350 degrees Celsius plus 273, we will get the 623. And we have the minimum pressure at point number 1, which is already calculated, which is 91.76 from table, which is the T saturation. So 91.76 plus 273, we will get 364. So we have the minimum temperature, we have the maximum temperature, then we can get the thermal Carnot efficiency. So the Carnot efficiency will be around 41.5. Means if we are going to operate the Carnot cycle between these two temperature limits, then we will get the 41.5% efficiency. So this is the maximum efficiency that can be achieved using these two temperature limits. And you can see our Rankine cycle is less. The efficiency of the Rankine cycle is less than the Carnot efficiency. If we are getting the efficiency more than the Carnot efficiency, then it means we are solving it wrongly, or there are some issues that we basically overlooked. So between two temperature limits, the Carnot efficiency will be higher, and no other cycle will produce more work than the Carnot cycle. So for this class, we are going to stop. For any question, you can contact me. Thank you.